This is Fluids Day 1. Fluids was added to the AB curriculum in 2002, and every year since, with the exception of 2006, there's been a fluids problem, so I would expect one on the coming test. The first topic is density. Density is the Greek letter rho, and it's defined as mass, which has to be in kilograms, over volume. So M is mass in kilograms, and V is volume, and volume has to be in cubic meters, and that will give us a density in kilograms per cubic meter. Densities in both liquids and solids can vary slightly with changes in temperature and pressure. The densities of gases vary greatly with changes in temperature and pressure, but for our purposes, we'll be using a constant density for fluids, at least with liquids. The specific gravity is defined as ratio of a substance density to the density of water. It is unitless, so if you had something, say for example, of a specific gravity of 0.4, then we could say that the density of that particular substance was 400 kilograms per cubic meter, because water is 1,000. Okay, the next concept we get into is pressure. And pressure is defined as force, which is in newtons, per square area. And area has to be in square meters. And when you do that, you get your pressure in pascals. Here's the first example. This says the red tar cat jasper weighs 72 newtons. If each paw is roughly 4 square centimeters, find the pressure exerted by one paw. Okay, in order to do this, I have 4 paws, so the force exerted by a single paw would be 1/4 of the overall weight of jasper. Of course, that's assuming it's equally distributed. That would be 18 newtons per paw. Okay, now the area of a single paw we've been given is 4 square centimeters. But as we've said before, if we're finding pressure, we have to convert this to square meters. So 100 centimeters is equal to 1 meter. But you notice we have centimeters squared, so we have to square this. So in terms of square meters, it's 4 times 10 to the -4th square meters. Now we can find the pressure exerted by a single paw. That would be the force exerted by a single paw divided by the area of the paw. So we have 18 newtons divided by 4 times 10 to the negative 4 square meters. And a newton per square meter is a Pascal. That is 45,000 pascals. Which is why when the cat jumps up on me, I try to get him to lay down, because that increases his surface area. Okay, now pressure does vary with depth of a fluid. All points at the same depth have to be at the same pressure. If they were not, the fluid would not be in static equilibrium, and it would flow from higher pressure to the lower pressure region. Okay, now this is a very important equation. Let me circle that. P sub 0 is atmospheric pressure. P is absolute pressure. And you have to know the difference between absolute and atmospheric and gauge pressure. They are all in pascals, however. So P is absolute pressure, and rho G H is what is called gauge pressure. Atmospheric pressure, as you know from chemistry, is 1.01 times 10 to the 5th pascals, which is 14.7 pounds per square inch. And pressure does not depend upon the shape of the container. As you can see from the diagram at the right, at all 4 of the locations A, B, C, and D, the pressure would be exactly the same because it's at the same depth. Some applications of this are the manometer, and the barometer. Here's an example using the equation that we saw before. During Superstorm Sandy, a tank holding oil that has a density of 0.7 grams per cubic centimeters was flooded with salt water, and that has a density of 1,025 kilograms per cubic meter. The oil is 10 meters deep, and the water is 8 meters deep, and it asks us to find the pressure at the bottom of the tank. Okay, so the very first thing I would say we would want to do would be to determine the the density of the oil, and the density of the oil would be 700 kilograms per cubic meter. It's basically multiplying by 1,000, and you should have that conversion memorized. Okay, so let's see what it told us. It basically told us that our density of oil was 700 kilograms per cubic meter. That's the density of oil. The density of the salt water was 1,025 kilograms per cubic meter. And we had oil that had a depth of 10 meters. And water that flooded the tank, which sinks to the bottom because its density is greater than that of oil, of 8.0 meters. It's open to the air, and we know that the pressure of the atmospheric pressure here is 1.01 times 10 to the 5th pascals, and that would be a great number to have memorized, although I do believe it is on the formula sheet. Okay, so we know at location P1, that's open to the atmosphere, so the pressure is 1.01 times 10 to the 5th pascals. Now, as we go deeper in the oil, the weight of the oil adds pressure, and so at point 2, the pressure would be what it was at point 1 plus whatever contribution we get from the oil, which is the density of the oil times G times the height of the oil. And remember, this 10 meters is what we're calling the height of the oil. Okay, so P2 would be equal to 1.01 times 10 to the 5th plus 700, make sure you're in kilograms per cubic meter, times the acceleration due to gravity, 9.8, times 10. So I found the pressure at point 2 to be equal to 169,670 pascals. Now at point 3, I have the pressure at the top of the water, which is P2, plus I have to add the pressure due to the water, which would be rho, which is for the water, G times the height of the water, or depth of the water, and this is the height of the water here, 8. Okay, so when I substitute those numbers in, I put in 1,600, 900, 670 pascals plus the density of the salt water, 1,025 times 9.8 times 8 meters. And so we find at the very bottom of the tank, the pressure 3 would be 250,112 pascals. So if we wanted to know the pressure at the very bottom of the tank, we would have to do that. Now you notice that every time I cross a boundary of different type of fluid, I have to start another problem. That's because the density of the fluid changes.